Good evening, welcome to another video lecture. This one happens to have the longest title that I think I've ever given one. In this video, I'll look at applications and special cases for electric potential and capacitors. This follows along and kind of wraps up chapter 19. We'll come back to capacitors when we look at electric circuits, but now they really connect well with electric potential and how they work. So here we go. So if we think back to chapter 18 when we talked about electric fields, and we talked about electric shielding, we looked at the idea of a Faraday cage where if you have some conducting shell or some conducting outside surface, within that shell, the electric field will be zero. Because this electric field will be zero, there's also zero electric potential within that shell. So on the inside of this, and I think of like a shell as like kind of like a balloon or something, but a conducting balloon. Inside that, there will be zero potential, and along with a zero electric field. Now, if we look at a solid sphere, a little bit different. We also, same thing, the electric field within the sphere is again zero. But the potential on the inside of the sphere is going to be the same as if it was same as just the surface. So if we have all the charge is going to be built up on the outside of the sphere, and it depends on how far away that charge is from the center, depends on like the potential. So because the charge will spread out throughout the surface, so this actually makes it become more like a point charge. But within the solid sphere, the potential is the same everywhere, same as if it was at the surface. Now, when we move outside of the sphere and we're looking from even a little bit away, or like as small as any sort of distance away, we can treat this sphere, as long as it's a sphere in nature, we can treat it as a point charge. And therefore, we have the potential depends on Coulomb's constant, the charge, and the radius, so KQ over R for the potential due to a solid sphere. The same would be outside of a conducting shell, but in this case, we're looking at a sphere, a solid one. So again, the difference between the two, within a shell that's a hollow inside, the electric field and the electric potential are both zero. Within a solid sphere or solid conductor, the electric field is zero, but the potential is the same throughout the entire solid object. So there's a little bit different there, and I'm sure that there is some type of question on like this on the AP exam. They love asking little things like this. But there we have it. All right, cathode ray tube. And we'll actually look at one of these when we get to magnetism, so it'll be a little bit different. But there's a cathode and there's an anode. And one is charged up positively and the other is charged up negatively. Anode is positive, cathode is negative. And what it does is that negative charge builds up on the cathode to the point that there's such a potential difference between the two of them, between the cathode and the anode, that an electron will actually jump off of the cathode and go shooting through this ray tube here. And it doesn't happen like randomly. That happens very often, consistently, like very, 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 very frequently when you have that happening. And that electron can either get deflected horizontally or vertically based on these deflection plates. Old TVs, old computer monitors, all had cathode ray tubes inside. And so that's how they actually created that picture, is it from shooting these electrons to where they would be on the screen. So, and we'll actually do a little demo probably next week about where we charge things up with a little capacitor and a cathode ray tube with the TV in class. So remind me, don't forget me to shock you next week. We'll do that. All right. Thank you very much for this one, and we're moving on to that next. All right, a couple little applications. So the first one is the capacitor, and we'll look at a little bit more with that, and then we'll look at some more electric potential. Within a keyboard, you have tiny little dielectrics in there, so that whenever a little capacitor down there in that dielectric, it holds this energy, so that when you go and you hit down on them, for example, here they have the B key, or if you hit another key, it sends out a little energy pulse. So it actually takes a little second to build up the energy and store that. And so that way, when you go through and you hit down on the key, it releases that energy and says, oh, I've hit this certain key here, and it goes through for that. When we have a cell, for example, a cell will build up a potential difference between two different layers. You have a positive side of the cell and a negative side of the cell, and within like your nerves, you can think that. And when they send a signal, there is a rush between some fluid of that extra charge moving from one side to another. And all cells will have some sort of positive and negative, will be releasing charge back and forth and be polarizing actually as different things happen. So as we have different, and this is more, I guess, goes into like the biology aspect. And I'd love to have a bio teacher come in and kind of talk about this a little more, because I'm not as familiar with it as I probably should be. But this is kind of like the main idea within a cell. And this happens all these things happen very fast over a very short period of time. But there's a potential difference within a cell for a positive side and a negative side, where some ions are released between two cells to actually create or change or cause a reaction within your muscles or with anything else. And that gets us into the next thing, which is an EKG. An EKG or an ECG, depending on what you do, it's electrocardiography. And so what it does, it measures the electric potential of your heart and in a graphical sense. And the graphy part is kind of electrocardiography, is the measurement idea. And what happens within your heart is, as different parts of your heart, different chambers, contract or expand, there are different electrical signals being sent out. And when they use a EKG machine, they strap on little sensors, different parts of your body, and they measure this. They measure your heart just kind of pumping away and doing its thing, and they can detect all sorts of whether you have a healthy heart or whether you have a smaller certain chamber, a bigger certain chamber of your heart, based on the pattern that it has. Now, in this picture here, the PQRST refers to different cycles within a different parts of the cycle. So one's one chamber opening up, one's another chamber opening up, and you can look up the specific parts of that on your own. I'm not familiar with the different exact which one corresponds to which chamber, but it goes through with that, and it actually measures this potential difference in this charge, this amount of charge. And what they do is they then compare it to a healthy heart or a diseased heart and different things like that. The last thing here is an EEG, which actually is used to determine whether people have a chance of epilepsy. And what it does is it measures the slight little differences within your brain. So what actually happens, and Mr. Weiser has a good story about this, but they measure it when you're asleep here, and they measure your brain function, and whether it's abnormal or normal, just back and forth, kind of the potential differences as different cells are interacting. So they've actually gone and mapped out for certain people that suffer from epilepsy, suffer from strokes, what it is that causes that. And then you can do it by, it can be whether it's bright lights or anything like that causes certain reactions for a difference. But from these different types of machine, these electrography machines, and measuring it, they can determine things. Within nature, there's also that sharks actually have the ability to measure the electric potential due to fish, small little differences, and they have that up near their nose. They actually have that ability there. They are able to detect that potential created by a fish as they're moving and they're changing and swimming around with their cells. So there's a lot of actual applications to this idea of electric potential and capacitors outside in the real world and within our daily lives. A couple quick questions from the video here. How are conducting shells and conducting spheres different? In this case, in respect to electric potential and electric field. And 2, where are cathode ray tubes used? And finally, what does an EKG measure and what can they detect? Thank you very much. Make sure to put the answers in online, and I will see you tomorrow in class.